5. Okay, so A1, we just talked about the basic vectors. Tomorrow your quiz covers basic vectors. Yes, tomorrow a quiz. Okay, would you like one big honking quiz, or would you like little snippets every couple of days to see if you got something so we can fix it before you get in too deep, right? Okay, we're going to do little snippet quizzes instead of one big honking big one. Make sure everybody's got it. Can somebody answer the door, please? Okay, so same thing from yesterday. We got vectors have magnitude and direction, but we already knew that, right? No big deal. For those of you who weren't here yesterday, I will give you the handouts from yesterday in a minute. You haven't missed much. Okay, and we already talked about writing them in component form, but now, see all these little vectors here? All the T, V, P, W, they're all equivalent. Remember equivalent from yesterday? They have the same magnitude, same direction, but are they in a different position? They're in a different spot on the coordinate plane, but we really don't care. As far as vectors are concerned, they are all equivalent because they all go right 3 up 2. Everybody see that? All same length, same direction. They all go in the same direction. So they're all equivalent. Now, the thing that's different now is that if we took this and we slid it to where P is in standard form. Remember, standard form for yesterday means it starts at the origin. So all those can be described the same way using the vector notation right here. So, hang on, let me show you. Oh no, I don't want that one. I want, here we go. They all can be described the same way, right? The delta x is 3 and the delta y is 2. The other thing is, if it's in standard position, that point, you can say it just has a terminal point of 2, 3, and that describes it. You can describe a standard vector that way just by describing its terminal point, because if it's in standard position, it starts at the origin, right? Yeah? Got it? All right, so we're going to write the vectors in component form. Now, it's not just going to be a drawing. I'm going to give you 2 points and make you find it. But if you have 2 points from when you were in Algebra 1, if you had 2 points, could you write the slope? Right? Okay, now instead of writing the slope, we're going to write it in component form where it's delta y and delta x. And Jaden's going to stop getting the giggles right now. Yeah, pretty much. Okay, this right here, this is the x and y. I don't like the way they do that. I prefer to do it where it's, I prefer to call it delta x and delta y. Why? Because that's what you're really doing. Whenever you do these, whenever you find the component form, you always go x2 minus x1, and then y2 minus y1. Is that delta x and delta y? So you're just looking for the change. And for those who weren't here yesterday, whenever you're writing a vector, the way we know a vector is different from a point is because it has the funky brackets that look like less than and greater than, as opposed to the rounded brackets. That's how we know if it's a vector. Okay, so if I don't have a drawing and I just have points, like in this example, can I find the component form? Yeah, because I'm just going to do, well, for this, right, these 2 points right here, I can look at this right here and say my delta x is equal to negative 4 minus 2. So it's negative 6, right? Does everybody agree? And then if I want to do the delta y is equal to what? 2 minus a negative 3, which means it's plus 3, which means it's 5. So if I'm writing it in component form, it is negative 6, negative 6, comma 5. And that's what y'all were doing yesterday. But y'all were doing it off of a graph. Y'all were counting squares. So yes, you have to be able to count squares. But you also have to be able to do it from a point. So that's what we're doing today. We're scaffolding from yesterday. We're just adding on that now you have to do it with a point or 2 points. But you've been doing this since you were, well, probably middle school. Okay, that's all great and wonderful. But there's this other thing we can do. We can also, if I give you 2 points, can you find the distance between the 2 points? You've done this since middle school, right? Pythagorean theorem. You can find the distance between 2 points because the distance between 2 points is just the hypotenuse of a triangle. This is that vector right there, xy. Notice that this is the y. That's the change in y. And this is the change in x, right? And we just found those. Can we find the hypotenuse? You'll realize that Pythagorean theorem and the distance formula are the same thing. Pythagorean theorem is c squared equals a squared plus b squared, right? Distance formula is c equals the square root of x squared plus y squared. So distance formula is just solving the Pythagorean theorem. So can we find the magnitude of that using the delta x and the delta y we just found? That's the nice thing about vectors. After you've done something, you actually use what you've just done. So if we want to find the magnitude of that, and if you remember from yesterday, magnitude was when you had, they do one bracket, looks like absolute value. I hate that because it looks like absolute value. I want you to do it as double brackets, if you don't mind. So I have vector xy, and I'm going to take, I want the magnitude, and I want to know how long it is. So I'm just going to use the distance formula, which is Pythagorean theorem, solved for c, and it is going to be the square root of, and then I'm going to take the delta x, and what am I going to do to it? Yep. Plus the delta y, also squared. That's going to be the square root of 36 plus 25. That is not going to come out nice. It just comes out the square root of 61, and we leave it just like that. So the magnitude of that vector is the square root of 61. The component form tells me the direction it's going. Well, it doesn't tell me the direction, actually. It just tells me what the vector is. The signs of this tell me what direction it's going. Does that make sense? You can tell what direction it's going because you see that it's going left 6 and then up 5. Does that tell you the direction? And this tells me the magnitude. I have just completely described the vector. But when you do this right here, that completely describes the vector anyway. But it gives me a little better feel for it if I have the actual magnitude.
Did you bring your button?
Excuse me?
Did you bring your button?
No. The new easy button. Yeah, that was easy, wasn't it? Well, let's see what the nose says, because somebody gave me this nose button, and it's like random.
Probably.
Yeah, probably. I'll bring it tomorrow. Okay. So now I have to figure out how to get this thing to let me. There we go. That works better. Okay. Here we go. Now, the glare's not too bad up there, is it? Okay. Okay, so we've just done magnitude and vector. Magnitude and direction. We didn't find direction. We found magnitude. And like I said, I prefer for y'all to write double brackets and put the little tick marks so you realize it's not the absolute value of a number, it's the magnitude of a vector. Get the difference? I don't like when they use notation that's something you know for something else. That's too confusing. So in here, we're always going to do double brackets, and we're going to put the little mark across it so everybody knows you're taking you're finding the magnitude of a vector. Got it? Okay. And we just did this, so we're just going to rewrite it so that everybody's clear that it's just delta x squared plus delta y squared. And don't sweat it, because guess what I'm going to give you on the test? I'm going to give you all of the formulas we need. You just have to learn to use them. Do you realize PreCalculus is a college math class? You signed up for it all year. Okay, so the next step, after we find magnitude, we got to find direction. And remember, direction's in terms of an angle. And they want it measured clockwise from the positive x-axis. What way did we go when we were doing a unit circle?
Clockwise.
Counterclockwise.
Counterclockwise. Whoops.
Yeah. So that's what's different is y'all are used to doing unit circle, which is counterclockwise, and now we're going to go clockwise. All right, from the x-axis. That's how it's defined. Oh, they did say counterclockwise. Never mind, I read it wrong. I'm a space cadet. It's just like on the unit circle. The difference is when we get into navigation. Navigation is weird. There's all kinds of different ways. But when we're doing this right here, fortunately, it's the same thing. Sorry about that. Okay, good. I should read my own notes. All right. So we just have to find that angle. So you got to remember back to what does it look like? So for that particular one, when we were doing this one, what quadrant is it in? So we look back at that one. Let's look at it. Look at this. What quadrant? If you put this at the origin and went up, what quadrant is it in? The second. You just have to keep that in mind. So if it's in the second, if I'm finding this angle, am I going to go from the positive x all the way to that vector and find it? Now, if I want to find the angle, and I know the x and the y, so I know the sine and the cosine, what trig function would be used to find that angle? Here, let me help you. If this is the angle right here, that's theta. And I have this is 5, and I have this is -6. If I have the opposite and the adjacent, what trig function should I use to find the adjacent and opposite? Tangent. Does that make sense? Right? Every single one of these, are we going to have a change in x and a change in y? So for every single one of these vectors up here, do we essentially have the x and the y of the triangle?
Yeah.
So if we have x and y of the triangle, we're going to use tangent every flippin' time. Every time. So let me recap on here. So down here, boop, 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 boop. For this, every single time you're going to have a triangle. So it's on the x, this is the x and y axis, right? And we're going to put in, suppose I put a vector this way. That means I've got a triangle right here. Yes, this is my change in y. This is my change in x. This is theta. And what relates those? Tangent. Agreed? So this means that tangent of that angle is equal to what? Here, let me help you. This is opposite. Sorry. Eraser. This is opposite. This is adjacent. So what is it going to be? Yeah. No. Yeah. Change in y over change in x. Isn't that cool? Just like slope. Turns out tangent is slope. We'll get to that later. Or you'll get to that later if you take calculus. You'll figure that out.
I didn't think we were still going to use this.
You don't think you're going to use this in calculus.
No, I
Sorry.
didn't think you were going to use this in
Oh, heck.
this semester. I thought we were done with that last
No,
semester.
no, no. I said we had to get through polar. It's trig functions. It's different than the unit circle, but it's not. You have to use it. We're using it still. Next unit, we start something new. Okay. Not really. We do algebra 2 again. Okay, so if you have this and you want to undo that to get the angle, how did we do that last semester?
Inverse of tangent.
Yep. So the angle is going to be the inverse of tangent of delta y over delta x. Way cool. Right? That's not too bad. So since we have this lovely triangle right here where we've already started the problem and we know delta x and we know delta y, how about we find the angle for that? Sound good? Here we go. So before I start, no, we're going to do this and then I'll let y'all play with calculators. Okay, so if I want to find that angle, I already know delta x, I already know delta y. I want tangent inverse. What was the delta y on that problem above?
Oh,
No, that's x. Yeah, 5
oh, that one.
over -6. We're doing this problem up here, right?
Yes, ma'am.
Okay, so we go in the calculator. And you have to pick. You have to decide if you want to do degrees or if you want to do radians. For right now, we're going to do degrees. So if we put that in the mode into degrees, and you put this in, this would be a negative 40 degrees. That doesn't sound right. That's what it would come out as. Okay, why is it coming out as negative 40 degrees? Do you remember why? Where is tangent inverse defined? Huh? First and second quadrant. I mean, fourth and first quadrant. Remember? Okay. So when it gave us an inverse, because this was a negative ratio, could it only give it to me in the fourth quadrant? But our actual one is not in the fourth quadrant, is it? Okay, so what's going to happen is it's going to give you an angle based on the inverse tangent, and then are you going to have to think? You understand what I'm getting at? You're going to have to translate that. This is in the second quadrant. So what this is telling me is that if it was a negative y and a positive x, it would put it like this, wouldn't it? And it's telling me that this is 40 degrees here. Right? Do you understand what I'm saying? No. Well, inverse tangent is defined in the first and fourth quadrants. Do you remember that? Okay. So if I have a negative ratio, it has to be in the fourth quadrant, even though our original one was in the second quadrant. Right? The original vector we had was in the second quadrant. The corresponding negative tangent, the thing that would give me the same ratio, is in the fourth quadrant. I don't want that one. I want that one. That's because this is where I really want it. So how do I get there? Well, so what I have to figure out is, this is a 6 and a negative 5 to get this 40-degree angle, right? Here, let me erase it and make it prettier for you. So I have 6, I have negative 5, and then I get an angle of negative 40, right? That's what that angle is. If I want the corresponding part up here, then what I need is, I need to go 6 this way, and I need to go 5 that way to get this angle. Is that the same angle? Do y'all see that? Yeah? So remember, what did they say? We're supposed to go positive from the x-axis. So remember how we did the whole unit circle thing? If I want to find this angle, and I know how far it is from 180, do I just subtract it from 180, and that's going to give me, because what angle am I looking for? I'm really looking for this angle. Is that the angle I'm trying to find? Because that, remember, it's based on the unit circle. It's just like the unit circle. We started at the x-axis and go around. So is that angle, the green one, is that going to be 180 minus 40? Do y'all see it? So the actual angle, and this is the part that takes thinking, is 140 degrees. Someone answer the door, please. All right, so that's basics. Now you got to go the other way. Now, what happens if I am given the component form, and I'm given magnitude and direction? Can I find the ordered pair for the vector? That's the next step. And here's the way it works. So this is supposed to be a little tick mark across the top. Oh, let me change colors. Okay, here's the formula. So the way, oops, come back here. So the way it works is there are these unit vectors, and we have to multiply the magnitude of the vector by the cosine of the angle. So let me show you what's going on. So I got magnitude of the vector times cosine of the angle. So think about what that the vectors look like? Is delta x the cosine of the angle for the triangle, right? Is that what the x component is, or the delta x is? And then if I multiply it by the magnitude, will that tell me how long that side is? And then not absolute value, magnitude marks sine of the angle, that's the delta y. So let's think about that. So we got our triangle, right? We're on the unit circle. We got some vector. I'm just going to do it the first quadrant to make it easy, right? So this is sine of the angle, right? Cosine of the angle on the unit circle. And what's the diameter, what's the radius of the unit circle? It's just 1, right? 1. There's the angle. That's from the unit circle. But now it's a vector, and it's not 1 long, is it? That's the unit vector, but now we've got, that's the unit circle, and now we've got a vector. It's got the angle, and I got a delta x and a delta y. How do I find it? It's the same thing as this, right? But now I've stretched it. And how do you, whenever you stretch something, don't you just multiply all the sides by that same coefficient, right? And guess what that coefficient is? It is the length of this vector, which is the magnitude, right? So going from the unit circle to this, do I just have to take this and multiply it? Do you see where the formula is coming from now? So this side is the magnitude of the vector times sine of the angle, because that sine gives me y, and this is magnitude of the vector times cosine of the angle. And once again, I'm telling you how to do this, but I'm going to give you this formula. But is that why are we starting with what we learned in the unit circle, and we're just expanding it? So we're just going to use this. So you now know how to find angle. You now know how to find magnitude. Can we put it all together? We're given something that has a magnitude of 10 and an angle of 120. Ready? So when we go to find that vector, it's equal to, hang on a second, I drew that wrong. It's equal to the magnitude, which is the 10, and then for the x, do I use cosine or sine?
Cosine.
So it's cosine of, and the 120 degrees. Is that going to get the sign correct on the coordinate? Do you understand what I'm saying? By putting the 120 degrees, is it going to put it in the second quadrant where it belongs? It is. And then 10 sine of 120 degrees. And if we put that in the calculator, but we don't really have to because I know what 120 degrees is, right? Is 120 degrees, that's going to be, the cosine's a -1/2 and the sine is square root of 3 over 2. Don't worry about it. You're going to have a calculator, but if it's exact values, you're also going to have a unit circle. So could you look it up? Yeah. So this is, if I'm saying in degrees, this is going to be 10 times, this is -1/2 because I'm in the second quadrant. And this is going to be 10 times the square root of 3 over 2 from the unit circle. It's a little messy, but it will live. And when I simplify that, because I can simplify it, right? Once again, you'll have a calculator. This is -5. And this is 5 square root of 3. So unit circle hasn't gone away, but it's not, you're now, if I require unit circle, you'll have one to look it up on, or you'll have a calculator. Okay, so from yesterday, we added and subtracted, and I showed you kind of the component form, but we really did it with like graphs. Now we're just going to get into the, okay, we're going to do component forms. So I'm going to give you two vectors. They're in their component forms, and if I want you to add and subtract without graphing now, we're not going to graph it. Is it just what we did yesterday? So if we want s plus t, are we going to just take the x components and add them? So I'm going to do 4 minus 1, and then add the y's, 2 plus 3. So it is going to be 3 comma 5. Was that easy? If I want to write it in terms of the i's and j's. Okay, so I and j is basically this. Let me show you up here. See this right here? If we're looking at this, hang on a second, let me get the green. If we're looking at this, is this vector made up of, if I went this way and then went this way, if I put those two vectors together, would that make that unit 1 vector? Right? This is I, and this is j. So the vectors that make up the radius of a unit circle, the x component and the y component, that's I and j, and they're called unit vectors. Okay, and we make up this with that. So can we write this as the same thing? Can we write this in terms of I and j? So it's just going to be 3i plus 5j. So to make that vector, does that mean they went 3 right and up 5? Is 3s minus t just as easy? 3s minus t. So take the x component of s, multiply times 3, what do you get?
Six.
12, and then, oops, sorry, forgot to do the, and then I've got to do minus t, which is minus 1, right? Minus t plus 1. Then I'm going to do 3 times the y, which is 6, and then I'm going to subtract t minus 3. Did everybody see what I did? I need to do it slower. Y'all got this? No? Okay, what did I do? Here's what I did. I did 3 times the 4s, and then I subtracted the x for t, and then I did 3 times the y, and then I did minus the x. Is that what they're telling me to do with 3s minus t? That gets me to 12 plus 1 is 13. 6 minus 3 is 3. And if I want to write that in the ij form, it's 13i plus 3j. Got it? Okay. Okay, so remember the unit circle has a radius of 1. And then there's a thing called a unit vector. It has a magnitude of 1. Okay, so basically, you know how it was the unit circle? Had a radius of 1? Well, a unit vector has a magnitude of 1. So is it just that whole unit circle thing? Right? And the question is, what part of the unit circle you're on? So unit vector is no big deal. It's just what y'all been doing, only now we're taking those and we're saying, okay, it's just so you can figure out everything using the unit circle, then you're multiplying by a scalar to get it scaled up. So whenever you're trying to find a unit circle, what do we have for magnitude? Right? Magnitude of a vector v was equal to the square root of the delta x plus the delta y, right? So What one am I doing? Oh, I'm doing this one down below. Okay, so basically, u is equal to whatever the vector is divided by the magnitude. So think about that. This thing is in terms of delta x, delta y, and that's the vector. So it's basically what they're doing is up here, see how we multiplied, this is I, and that's j. Have I just multiplied by the magnitude? To get back to the unit vector, am I just doing this to get back to I and j? So this thing is I times the vector magnitude, that thing right there. So what I'm starting with is v, that is equal to the magnitude times cosine of theta, which is I, and then it's magnitude of the vector times j, and now I'm doing divided, so that was what that was, and then magnitude of the vector. Do you see how you're just going to end up with I and j? Okay, well let me write a little different. Not I and j. How about cosine and sine? Does that make sense now? This is, let me rewrite this so that it makes a little more sense to you. This is cosine of the angle. This is magnitude sine of the angle. When you get done with that, are you going to end up with cosine of the angle, sine of the angle? And is that what we did when we did the unit circle? Right? And y'all know all those. And y'all can find them on the unit circle and you can use your calculator, right? Okay, so here, let me write, this is what I did. Right? I'm just writing the formula again so we can see it. So if we want to find the unit vector that has the same direction as that vector, so basically what we want to do is we just want to find on the unit circle that piece that corresponds to that vector. So what we do is we find the magnitude first. And it's going to be the negative 4 squared plus the negative 1 squared, which means it's the square root of 16 plus 1 equals the square root of 17. So if I want to find the units, or the unit vector, I'm just going to take each one of those parts and I'm going to divide by the square root of 17. So that means that the u vector, I did that wrong, hang on, that was messy, there we go, is equal to vector bracket negative 4 over the square root of 17, and then it's going to be negative 1 over the square root of 17. And we can't leave it that way, can we? You can't leave it with the square root of 17 underneath, can you? Do we have to rationalize it? Which means I have to multiply by square root of 17 over square root of 17, right? So I got to do square root of 17 over square root of 17, square root of 17 over square root of 17. And what's that give me? It gives me negative 4 square root of 17. Well, what is square root of 17 times square root of 17? 17, right? And this one's going to be negative square root of 17 over 17. And we just found a unit vector. Can you let an aria back in, please? Thank you. Okay, last part, and then we're going to have a work day tomorrow, just working on this. But I just want to get all the notes done so that I have it all in one. All right. Now, they're going to use different words, but are we doing the same thing? Shh. All right. So, back to the unit circle. See how I This is a vector. That vector I is the x is 1 and the y is 0. Because when we're doing this right here, for this, we've got a triangle, right? Coming off the unit circle with some angle. And this is I, and this is j. So we've got a vector that comes out, and it is 1, 0. And we've got a vector going up, and it is 0, 1. And those two make up a magnitude of 1 vector. That's where I and j come from. And then that whole magnitude thing is like, if you take this and you multiply by the magnitude, will you scale up that unit circle triangle to make the triangle for the vector we're looking at? So all you're going to do when you want to write an I and j component is just like we've been doing. They have all these fancy words where they want you to do a linear combination. All it means is write it in component form and then put the i's and j's in there. So do we need a delta x? What's my delta x? 5 minus 2 is 3. What's my delta y? 4 minus 2 is 2. Is this going to be my I component and this going to be my j component? Yep. So if I want to write as a linear combination, when they say that, as soon as they say of I and j, you just go, oh, okay. Then I want 3i plus 2j. If I add those two vectors together, will I produce the vector that's MP? That's all that is.